Let me introduce the speaker to you all again because many of you, if you follow the news, then you may know Dr. Chandrakanta Kumar, his name. Last year, he became famous due to the Indian ISRO's space mission Chandrayaan 2. Presently, he is the head of electromagnetic section of UR Satellite Center. But Dr. Kumar is from a very remote village. He is born in Shivpur, West Bengal, India. He received his both MTech and PhD degree in radio physics and electronics from University of Calcutta in the year of 2001 and 2012 respectively. He has completed his space studies program from International Space Universities, France 2013. After that, he joined ISRO in 2001 as an engineer. He primarily designed and developed the antenna systems for the Indian space program and related ground station. He has more than 50 international publications in the peer-reviewed journal, and he supervised 2 masters and 2 PhD theses. And not only that, he was associate as a project manager in the antenna system for Chandrayaan 1 mission, GSAT 12 mission, and also he served as a deputy project director for the RF system of Chandrayaan 2 orbiter. Dr. Kumar is now actively as a volunteer of IEEE, and he is the president and joint secretary of the Bangalore section. Today, Dr. Kumar will give his talk on the topic of linking space mission and few basic concepts or physics. Now, without not wasting much time, I want to request Dr. Kumar to please start your session.
Thank you, Dr. Meena. Am I audible? And my
yeah, you are audible. You are audible, loud and clear. Please.
Yeah, thank you. So to start with, I thank the Raj College, Jhargram Raj College management for inviting me, and as well as the Alumni Association. It's a privilege to be part of this talk. And when Professor Chaki told me that you have to give a talk, he requested me, then I was just wondering what to talk. So then Dr. Mrinal came into picture, then I in consultation with him, and whatever came to my mind, I thought I'll talk on this as topic, and I gave to him. And then it evolved over the time, and so now the title of the talk, what I could finally put is like this: on some basic concepts of physics and space mission. So before starting the talk, I must thank principal of Jhargram Raj College and HOD of the physics department for their support and encouraging word. From the words of the principal, I am feeling tempted to see Jhargram Raj College, because 300-acre campus, it's really wonderful. I can believe that one. So it should be beautiful in the lap of the nature. So to start the thing, let me start with the first slide itself. You can see the nice, and after picking up the topic, then I understood that I have to sell a refrigerator to Eskimos. Initially, I thought, okay, I'll talk something about physics, this, that, but then I realized when preparing that, okay, everybody is a physics teacher, so I have to sell a refrigerator to Eskimos. So that is the job I have taken on my this one. Because I believe my work of field of work is very narrow, and it's very difficult to convey to this one. So, and that's why I have confined those my work area of work into last 2 slides only. The last couple of slides will be on that. So whatever you have heard about me, just forget about all these things, because I may not be worthy of those things. So let me just put across my thoughts on the topic what I have tried to discuss with you. So you can see a nice picture here, and that is the picture what we see in the full moon day, the moon in the background of nice stars and all these things. Now, if you do the, if you see from moon how we look, how our home looks, this is how we look. So once it was asked to astronauts that when you leave the Earth, means when it's mission, what do you feel? He told, first thing what it comes to our mind is we become a philosopher. Means that time you understand that what is this world all about. Now, if I go to a little further, means which was the nearest celestial neighbor from our Mother Earth. Now, if I go to the next one, that is on the Mars. If I take our picture of our home from Mars, it's like this. Are you able to point anything here? So that is us. Where the cursor is, that is us. So this is how big we are. This is how big we are from our nearest neighbor, that is Mars. So within this, we are maybe 100 billions of living creatures, and our all knowledge, our all egos, everything is concentrated in this small dot. So if you enlarge this part, you can see this is our Earth and this is our moon. It is all concentrated in a small dot. So that's how big we are. So that's how makes me feel humble when I see this picture again and again. I took this picture from Dr. Gautam Chattopadhyay. And sometimes we say that we are in a space mission. That means we are going to space or something like that. So this picture actually gives you a feeling that we are indeed in space already. It is not that we are going to space. And Earth is nothing but a cradle of humanity. And mankind cannot stay in the cradle forever. With this small introduction of myself, I just slip into my thought. Hope I am audible, everybody. So the agenda, whatever I thought of sharing with you, that I just wanted to connect the basic science with our space mission. I felt that when I also was I am a student of physics. Even today, I am learning every day. So when we started learning the physics, there we used to feel that there may be some disconnect with respect to the concept of the physics and actual application. So with that thought, we started. Then we'll just see how we can leave Earth and reach another celestial object, and need of such mission, challenges, and if you want to have a manned mission, what are the other challenges you have to face. And in this process of challenges and constraints, and this provide the opportunities for the engineers and scientists to innovate in their design and implementation. That is all about my talk. So if I start with a simple concept that on Earth you go to a high-rise building, say, and you carry some of the stones with you, and you just throw horizontally some of the stones. So if you use some force, so it will reach some distance, maybe this one. If you apply some more force or some faster, if you can throw, it will reach some further distance. And depending on the energy that you impart, stones will go. But after some time, you can imagine, because Earth is a spherical object, so after some time, you can imagine that the stone, it may miss the Earth like this. It may miss the Earth. Then it will be always falling. Means it will not be able to touch the surface of the Earth, and it will be always falling. And if you throw even further, with further energy, then it will go even further away from the Earth's surface in this direction. So what happens? Now, when you are imparting just enough energy, then you are just missing the Earth. So this will be the way you will be following the Earth. This is the point of your release, and you'll be following the Earth like this. And in ideal condition, you're supposed to be in this orbit only, but because of some imperfection and all, this orbit will gradually decay and you'll be landing on the surface of the Earth after some time. Now, if you impart a velocity, it is that is dictated by this. G is the universal gravitational constant, m is the mass of Earth, and r is the distance means from the center of the Earth to the tower. So equal to this energy, then you'll be having a circular orbit, this orbit. That is the circular orbit, the minimum energy orbit that you can have with a velocity of this. You can see if you increase the height, that means if you go further above the sky, if you go above and high above, then your velocity requirements comes down. Because you can imagine when you are throwing the stone in horizontal direction, it is falling downwards with a gravitational pull, and it is moving forward with the velocity whatever you have imparted. So as you go up, so it takes more time to fall. So you can to travel the same distance, you have more time, so you can go a little slower. Now, if you increase the energy to a value that is called escape energy, that is given by gmm by r square, just exactly to this value, then your orbit will no longer be a closed orbit. Then you take a parabolic orbit. Parabolic orbit means it doesn't come back again into his place, so it will be open orbit. And if your energy increases even further, that orbit becomes hyperbolic, and you leave Earth. So this is how you can leave Earth. Now, when you leave Earth in the quest of reaching another object, so you have to hold your attitude. Means when you are trying to study something, so you cannot lose your focus. So in that process, the basic conservation of angular momentum and conservation of linear momentum, those two concepts drives the next part of the mission. That is from the release of the object to reaching the other part. Now, that is the linear momentum of the thing will be conserved, and angular momentum of the object will be conserved. Just if you want to reach one destination, it is not always correct that you will be always in the same path or the correct path. There may be some dispersion in the in between happening. So you have to correct this. So how to change these things? Unless you change your linear momentum and angular momentum, you cannot change your direction or change your path. So here I have put a picture of some nice balloons. They are just flying high and freely. Now what happens if you just untie one of this balloon here or you can puncture one of the balloon? What happens? The gas inside the balloon, it's come out through the nozzle or through that leakage addition hole, and it starts moving. The balloon starts flying opposite direction. So same principle is used. So your object or your satellite or whatever it is having an engine. So it starts burning that fuel and it ejects some gas and backwards, and its forward direction energy changes. So that's how, using the property of conservation of linear momentum, you can increase the velocity of your vehicle or object. Or if you orient the the thruster, this is called thruster, in a reverse direction, then your velocity can be reduced. So like this, you can change the velocity of the object. And to change the angular momentum, another parameter that you have to change the orientation. This is the concept, very simple concept. When the tops are not rotating, they will be lying down the way it is given here. But when it is spinning, it is very steady. That is nothing but your angular momentum is conserved. If you try to disturb this one, it will come back to its own place. So this is the way we try to hold the attitude of the object or the satellite in our spacecraft. So we put 3 such tops rather, in the name, in the technical name, flywheels in X, Y, and Z axis, and we rotate with a good speed such that they are stabilized and our full object is stabilized. And in actual condition, we use 4 of them, not in an orthogonal condition, in a tetrahedral condition. Because in orthogonal condition, if you have a x-axis one flywheel, so it will not have any component in y and z axis because they are orthogonal. So if you want to change the orientation of the spacecraft, it is not possible. So you have with some angle such that any of the angular momentum, if we change the velocity of the wheel with the electronic drive, So that has a reaction to the other axis, and you can change the orientation of the spacecraft. And in actual spacecraft, the 4 wheels are mounted in this condition. You can see inside the wheels, and it has a drive, electronic drive. If you deliver more current, its speed will increase, and if you deliver less current, its speed will reduces. So accordingly, its orientation you can change. So in a the object, whatever is flying, it's in an orbit, whatever is supposed to be free. So you can change this way the orientation and the velocity of the object to reach the final target. And this is how a typical mission profile looks like. So initially, the launcher, your whatever launcher you have, it will be launching the orbit into a elliptical orbit of a smaller dimension. Then every time this object comes to this perigee, so there this sort of engines, that is gas engines, will be ignited. So some thrust will be imparted, and more and more energy you give, the size of the orbit increases. You can see it increases. So its apogee height increases. Now, if you have to reach to a different planet or different object like moon, so the day you are launching your spacecraft, the moon will be somewhere other place. So you will be reaching to that place, the moon or Mars or whatever object it is. So in that time, you have to plan your strategy like such a way that in that time, so it takes some 10 days or 15 days for you to reach there. So your moon or that object should be in that particular close to that orbit. Now, when your object comes close to the targeted object, so there the gravitational field of this targeted object starts interacting or start pulling it towards it. But what happens if you have enough energy? You can just miss its gravitational pull. So you have to reduce your velocity when you are under the influence of the target object, that is moon or Mars. So you just reorient your thruster in the opposite direction of the velocity and again fire it. So velocity, instead of increasing, it will reduce. And if you reduce the velocity, the moon's gravity or the gravity of the Mars will capture the spacecraft, and then you'll be having a orbit, which is the biggest orbit you'll be having. And just you do the reverse maneuver, whatever you did around Earth, that is firing the engine in opposite direction of the velocity vector, then your size of the orbit will be reducing, and ultimately will be coming down to a lower size orbit, maybe 100 by 100 or something like that. Till your velocity will be able to maintain you in the orbit. Now, if you want to come down on the surface of the Earth, so you have to see that velocity equation. That is, you have to reduce the velocity below the orbital velocity. So again, you reduce your how to reduce the velocity. Again, fire the thruster in the reverse direction. So your velocity will be reduced from the orbital velocity. So you will start falling down, and there will be a controlled. If you can keep this spacecraft under control, that is using the control system and thruster firing, all these things, then you can slowly come down and have a smooth touchdown on the surface of the celestial object, whatever you are using. But it is very difficult job. It is not you can imagine, say, if you are having a moon mission or something like that, your distance involved is close to 4 lakh kilometers, and at the end, say last in maybe 5-10 kilometers, you have to estimate the distance within meters accuracy. Can you imagine a 4 lakh kilometer distance at a distance, the object has to estimate the distance with the accuracy of 4 lakh kilometers, in meters. So that is the challenge that we have, but the basic physics remains the same. So how to implement that one, that is a different job. And that's how you can reach another planet. And because in the most of the planet there is no atmosphere, so there is no most of the cases there is no help of parachute or anything like that. So it has to be most of the time we have to depend on the thrusters. Now, how in the process of reaching there, how will you reach? See, if you have to reach a certain place in Kolkata or Jhargram or Bangalore, nowadays we can use the GPS. But just think over it that beyond some distance, maybe 2 lakh kilometer maximum, as of now, there is no GPS signal available. So how to navigate it? So for the navigation, we use a very interesting concept. It is nothing but the Doppler. Doppler we have always studied in our colleges, even schools also we have studied, and we have done so much maths, but we have seen that whistle blowing of a train, that is the maximum practical thing that we have come across about the Doppler. Now to navigate the spacecraft, so you first know where the spacecraft is. So to do that, you have to derive this information from the spacecraft. Then you need to know where it was supposed to be, such that you can think that, okay, this is the error that has come. So for that, you need to have prior computation or simulation available with you. And how to correct it? Correction is nothing but implementation of thrust, reduction of the velocity, increase in the velocity, change in the orientation, include using those wheels or some thrusters. These are the things you have to have. Now to know where is the spacecraft, what is the means? It is a very simple concept. Just send a carrier. Carrier means like a RF signal, some pure carrier. You send it. It will be received by the spacecraft and it will send it back. And you observe the delay, whatever it takes to come back, and that will, you know, the speed of the light, and that delay will give you the range. But distance is not enough, because it is a three object floating in 6-dimensional space. So you need x, y, z, and velocity along all axes to exactly pinpoint where the object is. Now, if you can, now you have to angular orientation. If you have to find it out, you have to find out differential delay. If you observe the Doppler, that is the change in frequency, you can get the radial velocity. If you can observe the Doppler for longer time, you get the radial acceleration. And if you integrate the Doppler over time, then you can derive the same carrier. With the same carrier, you can do all these things. But let us do delay is very simple. You can just send some of the frequency and just see that phase of the return frequency and the phase difference between the received carrier and transmitted carrier will be giving you the delay. There may be phase ambiguity, because it may undergo multiple 360-degree transition in the travel path. So you have to have multiple different frequency tones, and with that you can unambiguously derive the range using very simple formula. And if you have two ground stations on Earth receiving signal from the satellite, and they are quite wide apart, that is the distance between these two stations is big, it is maybe 4,000, 5,000 kilometers, that sort of distance I am talking about, or 6,000 kilometers. And if you can observe this delay in reaching the signal to this, means these two ground stations are time synchronized, means their times are very nicely synchronized using some radio stars or something like that, standard source. Now, these two ground stations receive the signal from the same satellite and observe the time delay to whatever they can record. So that time delay, that is delta tau into c, that is the light speed of the light, will give the difference in the range, that is the delta rho. Now from this delta rho, using this equation, you can get the angle of the spacecraft, that is the psi. So you just observe, you are just observing the signal from two ground stations, and from this calculation you can get the orientation of the spacecraft. And if you can observe the Doppler, that what I was talking, that Doppler will give you the radial velocity of the spacecraft. And if you integrate the Doppler, means you watch the Doppler over the time, that is, this is your velocity. So velocity, if you integrate over time to time interval, velocity into time is nothing but distance, And difference between two distances, that is T1 to T2, is nothing but range. So that will give how fast your object is moving. So using all these things, all these tricks, you can observe the spacecraft for a certain time. Say here you can see in the blue arc, I'm started observing the spacecraft from this point onwards, and I have using all these techniques I was observing, and I was just trying to find out the velocity, the position of the spacecraft. And I have another information, that azimuth and elevation angle of my ground station, and the range of the station satellite from the Doppler, and gravity model. Gravity model becomes very important when you are in space mission. So when you are close to Earth, only Earth's gravity you have to consider. But when you go a distance where gravity of Earth is very weak and you are getting into the gravitational field of other objects like Moon or Mars or other things, so there you have to consider multiple gravity, and you have to generate their model, and you have to apply those corrections, and you'll be getting the extrapolated orbit of the spacecraft, and then you can predict where it is going, and accordingly you can apply the corrections. So when you are ready to go using this sort of experiment, this sort of calculations before cutting in the material, so then you have to go prepare the mission. So preparing the mission is it's a very iterative job, not a very difficult job. I should not say it's an iterative job, because launching every gram is very costly. So you have to keep the mass in check, and depending on your mission object, your mass get restricted. That is, you cannot launch whatever amount of mass you want. So you have to carry some fuels depending on the distance you like to travel. And the space available for putting into all these things are very limited. You can see the black outside boundary you have to put. This is the actually area that the rocket provides you. So you have to fit everything into that. And when it is launching, it is nothing. You cannot imagine how means how it shakes actually. You cannot imagine that one. So it has to undergo that sort of load, and it has to maintain its integrity. And one thing you have to understand, that there is no scope of repair. Once it is launched, it has to work. So we have to take care of redundancy, means if one system fails, how other system to take care. And for deep space mission, manual intervention is not possible. For closed missions, you'll be able to watch the spacecraft and you can see what is happening, and you can be correct. But when you are talking of a very large distance like Mom and all, where the signal takes 15 minutes one-way travel, so half an hour back, after half an hour, only you can intervene. So by then your spacecraft will be dead if it is some critical. So your spacecraft should be intelligent enough to take some decisions and maintain its safety. And outside space environment is very harsh, like hard vacuum, and all these things will be coming into picture. Now, to understand how hard this environment is, you just imagine that you are burning something on Earth's surface. That is, the heat generated by heat released by this burning process is distributed in three modes: radiation, conduction, and convection. Moment you leave the Earth's atmosphere, your most favored mode of heat transfer, that is convection, is stopped, because there is no air to circulate or there is no liquid to circulate. So convection stops. So whatever energy, heat energy is generated here, it has to be, because if it is captured here only, then it will burn out. So if it has to radiate the energy, it has to be radiation and convection. You just imagine that you have a laptop or computer CPU. Just imagine a small thing that that fan of the CPU is not working. So after some time, it will heat up and it will stop functioning. And if you want to take it to even further, you just put your phone or something like that in a belcher and try to extract air in between, and you just see how it operates. So it will burn out after some time. So in that case, so you have to start your redesigning the PCB. You have to analyze all the places of your PCB where the heat dissipation is more, this red color region, and accordingly you have to distribute the system at different places. So whatever in your phone you are seeing in hand size PCB, that will become 3 or 4 times of that one, because you have to distribute all the systems. Now to enhance that heat transfer with conductions, so thermal grease we call it, to reduce the friction, because when you place one object onto other, there will be in between gaps, and those gaps in general in air, in ground, it will be filled with air. But when you are outside, so there will not be nothing, so heat transfer will not take place. So you have to fill all these gaps with some material that is called thermal grease. And wherever energies are more, thermal energy generated is more, so there you have to increase the thickness of the metal block such that the heat capacity of that place is more, such that rise in the temperature is limited. And you have to apply proper fins and black anodizing to help with the radiation process, that is to increase the emissivity of the material. And another nice thing, you just imagine a satellite in orbit, like here it is an International Space Station. So sun will be always one side. So one side will be always illuminated by sun, and that side will reach a temperature of 400 plus K. And other side, what it is there, it is nothing but cold sky. So it is 4K. So one side is 400K, other side is 4K. And your spacecraft is nothing but 2-3 meters or 5 meters at the most. So one side of a 5-meter vision is 400K, another side is 4K. So how to manage this environment? So for that, what it has to be done, you have to isolate the full spacecraft. It has to be wrapped with a MLI such that no heat exchange happens with uncontrolled heat exchange happens with the environment. And you have to put proper heater where it is getting cold. After analysis, you have to find it out. And where it is getting heated, there you have to make necessary arrangement for conduction or radiation of the heat. So this went with respect to the heat energy when you are living out of the Earth. Now, our magnetic field of Earth, it's like a mother's womb, I should say. It protects you from everything. What is that? No, this magnetic fields, it is nothing but magnetic line fields. Our Earth or any celestial object is continuously getting bombarded by high energy particle. That is one setup called galactic cosmic ray, that is generated due to supernova explosion or whatever it is in a distant object. And sometimes radiations from the sun, that is when the magnetic field of the sun will get detached from the sun's surface. So it will come out with huge amount of mass, corona mass ejection. And those particles will be high energy particles will be ejected everywhere, and sometimes it will be reaching Earth's surface. And because of the Earth's magnetic field, those things will be channelized to your north and south poles, and we'll be seeing some lights there, different color of lights. So those are the very beautiful scene, but that's nothing but the channelization of this energy. But if you go beyond these things, so you have to, your spacecraft or your object will be bombarded with all these things. So what will happen? It will upset you, means whenever some high energy particle hits somewhere, it will try to take out some electrons, or if it is very high, it will take out the proton from that particular place. It may damage, so if it is a logic device, that is a chip or something like this, it will upset the memory bit, plus become minus, all these things, 0 become 1, 1 becomes 0. Then physical damage of the components, so like you have a BJT or something, so junctions are there, so and junctions is punctured by a high energy proton, and sometimes this energy charged particles will get accumulated on the surface of the dielectric materials, and it will discharge in a single shot, and that huge current will flow. And if you are in a manned mission and you are having such a high energy mission, and if you don't have proper protection, then that mission is gone actually. So you have to use proper component selection, radiation shielding, then correction logic, and properly design your mission such that all these things can be avoided. And of course, you have to have redundant systems. And once we call the reliability is it's a practice rather. Like as there is no scope of repair. Like if your car is not working, next day you call a mechanic or take this one to mechanic and you get it repaired. But there is nothing like this possible. So you have to take care of each and every component, and you have to arrange the component in such a way that if there is a weak component, like here, its reliability is only 0.6, all other are highly reliable component. So you don't put them in your series connections, because in series the connection of the total chain, reliability of the total chain reduces because they simply multiply. If this is 0.9, this is 0.9, and this is 0.6, you can see overall reliability comes down below 50%. So there you have to adopt proper topology, like you have to use them in parallel connections, such that the overall reliability, in spite of the weak component increases, you can see it becomes more and more reliable. So this sort of engineering approaches you have to take. Now, when you are in a mission, what do you carry? Means when you are going out for a trek or something like that, what do you carry? So that depends on your mission objectives. Completely depends on dictated by the mission goal. So you, of course, you'll like to carry a camera of appropriate nature. Appropriate nature means if you're going out to a scenic place, so you'll take a normal camera. But if you are sending a mission to a sun or something like that, those cameras are of no use. So appropriate nature of, but you want like to have some photographs, because that is the first impact that makes into our mind, the photographs. Now, for scientific mission standards, some of the standard things that I could mention is some spectroscopes that the students must be aware of spectroscopes. So every object emits some particular lines. So depending on the target object, you have to choose the spectroscope. And X-ray, gamma ray detector, because all the sources means like galaxies and all these things, they emit in this X-ray band, gamma ray, this frequency. Actually, if you see the our sky in this frequency band, it'll be maybe thousands or billions, millions times of brighter than the normal whatever we see in naked eye. So you can have some radio sounding applications. You can carry radars, magnetic field measurements, and if you are going to land into that particular place, then you can carry some experiment for in situ analysis, like a laser spectrometer, laser for burning the soil there, and with the whatever gas comes out, with that you can analyze using spectrometer, and geophysical thermal measurements of the soil. And in the commercial applications, like we do geosatellite, geosynchronous satellite, and IRNSS or GPS, you can have a relay transponder, positioning, timing, accuracy, like cartographic measurement. These are the normal standard this one. But scientific missions, it is completely dictated by the imagination of the scientist and what they want to carry. And they can be comprises of all these things, or even totally different this one. So this is the some typical payloads that a mission carry. You can see one terrain mapping camera. This is TMC. That means it is a 3D picture. It gives a 3D picture. That is your height of the place and depth of the place is very important. So we need a 3D camera. Here you can see this is a instrument to study the emissions emitted by the sun or the corona of the sun. And here we are interested in detecting the water. So we had a spectrograph in that particular emission band, OH hydroxyl and H2O emission band. So depending on that, we have to choose the detector or the filters for this particular frequency, emission band. Then there are main material that builds a rock, that is magnesium, aluminum, silica, all these things. They also have a particular frequency what they emit. So at that frequency, we have to have some different just to analyze the chemical composition. So if you want to map different ice, it's synthetic aperture radar at S-band is very best choice. So depending on that. So if you want to analyze the neutral molecules available in this atmosphere, so you for that we have an experiment. So like this, you choose your experiments, and when you are landing there, so you can drill in that place, or you can use some of the sensor that can physically touch the soil, and they can measure the thermal conductivity, chemical compositions, whatever we can imagine on that. This one. Now, science mission and space mission, science objective and space missions are always interlinked. And till now, whatever I was telling, just what is the driving force behind the missions, driving equations or driving basic physics behind the mission. Now, sometimes missions also, space missions also drive the physics in the advanced level. That is to understand the basic how this universe was created. It's a continuing journey, questions. It is not yet answered definitely. And in that process, we send like Hubble telescope. It was launched in 1990. Then it was followed by Kepler. It was observing stars, and it has detected many habitable space, planets. Habitable planets means in our current consideration, we think a planet is habitable where water can stay in all his three forms, that is gaseous, liquid, as well as solid form. So those are the habitable range we call. So we have identified many habitable planets. So those are very important to answer the second question: are we alone in this universe? And then it is getting followed up by James Webb Radio Telescope. And as you know, if the signal is coming from the very close to the T0, that is the time of Big Bang, it will have more and more redshift. That is nothing but Doppler shift, but because it is ever expanding universe. So that redshift, the frequency will be shifting towards the red spectrum, infrared side. So this James Webb Telescope has been designed to that infrared region, and it is expected to probe up to the level when initially the stars and galaxies are being formed up to this level. And Hubble used to probe up to this level, that is advanced levels of galaxy formation. And we are here already, galaxies and everything are formed, and we are observing from this distance. And the means oldest signal that we derive, that we receive from this one, is nothing but cosmic background radiation. That is CBM, that is a 4-degree Kelvin radiation. Whatever radio noise we get, that is the furthest signal we can get. Now, apart from these things, we have some, when you are floating in space, you are in micro-G, there is no gravity. So in that condition, you have some experiments, that is crystal growth, and some medical experiments that is being performed. And there is some thought of mining some of asteroid to extract the valuable material, and possible setting up of this one for further human exploration. Now, when you are getting into the manned mission, so it becomes really multidisciplinary. And here, failure is not an option. Here, specifically, failure is not an option. In your scientific mission or whatever mission, you can fail, you'll be losing money. But here, though you can lose money, but you cannot lose a human life. So it becomes very critical. So it becomes a truly multidisciplinary in nature, not even interdisciplinary. So all streams of basic science, chemistry, physics, biology, mathematics, whatever you can imagine, those are involved. Engineering streams, whatever is there, I don't know, and some new engineering streams has to be set up for this study. System engineering, like life support system, mission design, medical science, psychology. Can you imagine that psychology plays a large role in this sort of mission? Food processing, ecosystem design, many more. And radiation from the solar flares and all these things that we told, when you are in a manned mission, this is one of the prime concerns. You cannot expose the humans or any living mission to such radiations. So it will be catastrophic if you are exposing without any protection. And for a manned mission, you should have redundancy. I was talking that if one system fails, another will take over. So that is we call dual redundancy. But it is not enough. It have triple and quadruple level of redundancy, including design redundancy. Means one of the device is designed by me, another designed by somebody else, as the two designs are completely different. So that sort of philosophies we have to adapt, and you have to provide emergency ejection system, protection from radiation, and pressurized cabin and space suit. Those space suit are very heavy, 20-30 kgs. They have to wear it. Maintaining oxygen and carbon dioxide level, and to the required partial pressure. It is not that you put only oxygen, take out carbon dioxide. It's not like that. You have to maintain the partial pressure. And if some impurity gets into the air, you have to immediately remove them, supply of potable drinking water. And when people are confined in a small area, their moods will change like anything. So that proper training of the astronaut. And because you will not be undergoing a normal cycle of 12 hours day or 12 hours night, circular orbit will be always orbiting like ISS orbits around every 2 hours or even less, 90 minutes. So every 90 minutes, your day and night will change. So you'll not be, your sleeping condition will change, and it will be constantly noisy environment. It affects the human psychology. And for a manned mission, there is some physical effect. Actually, there's a lot of physical effect, because you'll be normally you'll be in 1G condition. When you are going to a floating platform, you'll be 0G condition. Then if you are going to moon, it is 1/6 of G. And if you are going to Mars, it is even, I think it is exactly half or something like that. So in coordination of your hand, eye, and your head, you are thinking that I can jump its ditch. But when you jump it, you will be going further, or you may not be able to jump. You will be falling in between. So that sort of coordination will be required. And it is, you cannot pull something when you are in floating conditions. So those sort of adjustments you have to do. And because your body structure is not feeling the weight of your body, so your muscles or bones will not be growing, so they'll be decaying. Almost 1% of bone mass will be lost every month. And 1% is the general this one loss of bone for a person beyond 60 per year. So in this age, you can imagine this sort of, if you are in space for 6 months, you are losing 6% of. So you have to take adequate precautions for that. And whenever you are not there into the gravity, so your whatever fluid, that will not be coming down, it will be going upwards. So your pressure in the eyes will increase, and moment your blood flows out towards the brain will feel that there is enough blood, so it will stop producing the blood. So after some time, it will be scarcity of blood. So, and because of the decay of the your bones, so there will be a lot of calcium will be going out, and that may lead to kidney stones, and many different problems may create. And you can see this is the right side on the astronauts are being recovered. Actually, this is shown as a glorified vision, but actually, if you leave that astronaut as such in this one, he or she cannot walk on her own and go come back to his place. So he has to be assisted because of all these conditions. So with that, I told you that I have in last couple of slides what I do, because I do a very small part of it. So you can imagine that we have to have a continuous communications with the spacecraft when you are in a mission. And for the only way to get connected to the spacecraft is through the RF link, radio frequency link. And for radio frequency link, there are three components: receiver, transmitters, and antennas. And receiver receives the signal, transmitter transmits, and they operate through the antennas. Antennas are like ears and eyes of the spacecraft. The signals get into through them. And when you are very close to Earth, then you need an antenna that covers a large part of the coverage area. So that time gain of the antenna should be small, and its coverage should be big. So we call it a low gain antenna. And moment you go little further, that coverage requirements comes down. So you can have a limited coverage antenna, and you can increase the gain of the antenna. And in some cases, you can increase the gain of the antenna even further, such that your powers are required power is less. Like in a Mars mission, sort of interplanetary mission, initially what I was explaining, that you initially revolve around the Earth for many days. So that time you will be having a lower gain antenna. As you go away and away, you need higher and higher gain antennas. So in my work, I designed some of these antennas that has been used in many space missions. So this is the job that I do, and my team does this full, we call it transponder, that is receiver, transmitter, antennas, all this put together, and we provide the full communication systems for a spacecraft to communicate with the ground station all the time. So you can imagine that understanding the basic physics always helps you. Being a student of physics, I also studied my physics from Belur Archimission. So it is always fascinating when you can analyze a situation that is non-nominal situation with the light of physics, physical concepts. That is very easy instead of getting into the engineering first. And in the quest of learning the birth of universe, or searching life in outer space, the space missions plays a great role. And space mission is truly an interdisciplinary nature. You cannot say that I am electrical engineer, I am a physicist, I am a biologist, I am this one, so I need not be part of this one. It's not true. You imagine any stream that is required for a mission of a big stature. And as I told, in a space mission, reliability and fault tolerant systems are the major requirement. Means you cannot. There will be failures. Some of the components will not last as you might have expected. So, so you have to have an alternate plan for that. And of course, it's a costly affair too. So nowadays, all space mission, that is mainly scientific mission, no nation is going alone. There, because science is developed for full humanity, so they are trying to collaborate with many nations and trying to have a bigger mission, such that it can derive some meaningful science out of it. So with this, I think I conclude my I stop sharing my thought. I hope I could convey what I wanted to, and it is useful to the audience, and I think I am also on time. So thank you very much once again, and for giving me this opportunity. And I also see Dr. Bhattacharya has joined this panel. So thank you very much, sir. I am also looking forward to listening to you. And maybe sometime I'll be joining through laptop, and then I'll be switching over to this one, because I'm eagerly, after seeing that topic, I was more fascinated in listening to that. It becomes that way. So with that, I hand over to Mrinal to take the proceedings forward. Thank you all. Thank you.
Thank you, Dr. Kumar, for your nice talk. Most of the physics that you explain is very tough to digest. Most of the people, like me also, as I mentioned earlier, that I had diverged to physics 12 years back. But some of the pictures, it's very common to us due to the YouTube, particularly from some videos of Dr. Sunita William. He used to upload in YouTube. But after overall, I believe this is a very informative session, and I can see many comments in the YouTube live chat box, and people really enjoy that comment. And if you have permission, I can request our faculties, other personnel who are available in the panel now, they may have some question.
Yeah, please.
Okay, may I ask our faculties if you have any question, you can please raise your hand using the Zoom raise hand option, and I can go to you. Please check the raise hand option. While that time, I have one question that is actually I received from many people that is actually related to the Chandrayaan mission last year. Since you are the part of that mission also last year, what was the feeling or situation in your team when you missed just from this small distance? Can you please tell all of the viewers? Viewers actually wanted to know that.
Yeah, I think that is just exactly 1 year back. It was on 8th September.
And one more coincidence I want to tell you, not only your name, but also the time when you start to speak, that is around 2:43. That time the Chandrayaan 2 takes off. That time, the coincidence after coincidence with you.
Yeah. Thank you very much for watching this one. And that experience probably, I hope that no other person should experience that one. But actually, we are totally blank at that time. Yeah. Totally blank, because we also was not able to feel what not to do. So all of a sudden, out of a lot of anxiety, all these things, just if somebody was lot of pressure and all of a sudden it was means you don't know it, like somebody jumped out of the rooftop and he's falling, and it's that sort of feeling. And of course, it was not a very good feeling. So that's all I can share. But I hope nobody else go through that one. Though it is a part of our life, but it hope that nobody goes through that.
Exactly. I hope in coming future we may see many success missions conducted by ISRO. Well, I have one more question. Actually, it is came for one student. He is a class 12 student. He's asking that if he want to pursue his career in ISRO or in space agency, what will be your tips for that student? How he can prepare from his class 12?
As I told, the opportunities in space, this one is enormous. And probably if you confine to the Indian perspective, it is a little restricted. But if you are going to some other space agencies, there, that's what I was telling, even starting from psychology to biology to bioscience, anything, any stream you name, even there's history, literatures, all these people are also required. The only thing I can tell the students, whatever you are doing, you love doing this, love doing that. Whatever physics, chemistry, or anything, you have to love that one. And there is always some process to enter into these things. So that is the secondary, I feel. So because once you get into that process, your love only will drive, your passion only will drive. That time your whatever you have learned, those things, again you have to, some of the things unlearn, and again you have to learn new things. So that passion only will drive. So study physics, chemistry, and maths, of course. Well, that is the main area, core area. But if you are in some other area also, there are scopes of getting into all these fields. So I'll suggest that try to love whatever you are learning.
Yeah.